All right, so here we are. Chapter 6, Section 1, Standard Normal Distribution. In fact, inside your book, it's called the Probability Distribution for Continuous Random Variables. And here is the transition from discrete probability distributions, where our numbers are whole numbers and they're countable, to continuous random variables, meaning continuous variables such as time or height or weight or anything like that, where basically you have like a decimal point. Now, the key concept that we're going to be looking at, and this isn't just for this section, it's kind of the entire section overall. The entire chapter overall, is going to be examining the standard normal distribution and its properties. And there are three properties for this. The first is that the standard normal curve is bell-shaped, so it's going to look just like this. Okay? Second, right down the middle is going to be our population mean, and that's going to equal 0. And then the deviation population, sigma, is going to equal 1. And this is for a standard normal distribution, okay? We have just a normal distribution. In other words, the word standard is missing, and you're going to see how that works, all right? So we're going to develop the skill to find areas corresponding to various regions under the graph. And we're also going to look at z-scores, and we're going to use them a lot from here and now until the end of the semester. All right, we're going to be using z-scores or critical values later. You're going to hear me say that a lot in chapters 7, 8, 9, 10, and 11. But we're going to be using those values to compute areas under the curve, okay, or areas under the graph. So the first thing I want to go over is, well, what is a continuous random variable? So a continuous random variable has a distribution Sorry if my dog is barking in the background. We have a Roomba that is currently vacuuming, and he just doesn't like it, I guess. So a continuous random variable has a distribution with a graph that is symmetric, and that's extremely important. All right, that is symmetric and bell-shaped, which we've seen that before. And it has this picture right here, all right, which is what I just drew up above. Mu equals 0. Our population deviation equals 1. And the formula to actually get this curve is right here. Now, this you do not have to memorize. I just put it there because that's what it is, all right? And the idea behind this is... Sorry, that's the vacuum going off in the background. I'm going to pause. All right, I'm back. So that crazy noise, if you heard it in the background, was the vacuum for the Roomba. But anyways, the idea behind this is that the area under the curve, so if I were just to draw some random line and just kind of like shade this in, all right, what we're going to be interested in is what is that area right there. Now, because this is a curve, there is no shape or no formula that we can use to actually figure out the area. For example, the area of a square is just length times height. Because if you think about a square or a rectangle, it's length times height. All right? Now, if you cut this in half, notice right here, the shape is a triangle. So the area of a triangle is equal to 1/2 length times height. Okay? Unfortunately, if you look at this shape right there, it is a curve. This part right here is constantly bending. All right, it's different. And this is a nice rigid line, and this is a straight line. But the fact of the matter is, there is no formula to actually calculate that area. So what we got to use is technically calculus, which that's beyond the scope of this course, and that's fine. But we have formulas that help us how to do this. And there's a lot that we know about this standard normal curve that we have above. All right. So I think a really good concept then would be, you know what? Instead of starting with this normal curve, which is, bell-shaped, why don't we start with a uniform distribution? Okay? Now, here are two extremely important properties about a uniform distribution. First, the area under the graph. And 2, there is a correspondence between this area and the probability. So when we talk about a uniform distribution, it literally is a rectangle where this could be like, let's say, A, and this could be B. So it's just the start of the rectangle and then the end of the rectangle. And then the height of this rectangle is the probability. And if it's uniform, that means the probability is going to be the same from A to B. And we could easily find the area of this curve, or basically this rigid object, by saying area equals the height times the width. So let me get more specific here. All right, so this is going to be my width and this is my height, okay? And a continuous random variable has a uniform distribution if its values are spread, keyword, evenly over the range of possibilities. The graph of any continuous probability is called a density curve. All right? Now, when you think of density, maybe you should be thinking of, let's say, a balloon, all right? We've all blown up a balloon before, and we know that when we put air into the balloon is very light because we're just putting in air. However, if we take that same balloon and we fill it up with water, it's heavier, and that's because water is more dense than air. So what we're concerned with is what is the stuff that we're filling it up with, okay? Now, because the total area under the density curve is equal to 1, there is going to be a correspondence between area and probability. Now, if you're asking yourself, well, where would we see a density curve like in real life? I think a really good example is our cell phone charger. We know that no matter what electrical outlet we put it in, we plug the cell phone charger into our house, at school, at work, wherever, that cell phone charger works. And that's because the voltage that is coming out of the electrical socket is about 110 to 120 volts. It's somewhere in between there. It's not perfect, but it's consistent. So you are expecting that voltage to work for your cell phone charger, and that's why it is the way it is. Okay, so here's an example right here. All right. So during certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes, which can be found on the next page. All right, so there's a picture right there of it. All right. Now, when we look at this, I want you to notice something. First, the waiting times is on the x-axis. That's our variable. So the variable always goes on the x-axis. Also, on the y-axis is our probability. All right. So if we think about what's happening in this problem, okay, you have five possible outcomes. All right. You can be waiting for, and I already forget the question now. Let me scroll back up here. You could be waiting for 0 minutes. So as soon as you get to the airport, boom, your airplane's there. Or you could be waiting for 1 minute, 2 minutes, 3 minutes, 4 minutes, or 5 minutes. But the idea behind this is that the probability that you get any one of these is going to be 1 over 5, which is equal to 0.2. Okay? In other words, each number, whether it is 1 minute, 2 minutes, 3 minutes, 4 minutes, they all have the same outcome, which is 1/5 or 0.2. So right here is going to be our density curve. That's the area. Now this area is going to equal 1. So now I need you to convince yourself that it is equal to 1. Well, if you think about it, area equals the width multiplied by the height. We know the width goes from 0 to 5, so that's going to be 5. The height is 0.2, so that's going to be 5 times 0.2, which is 1, okay? So that is what we're saying down here in the please note part of this question. Please note, all the different possible waiting times are equally likely. That's what makes it uniform. 2, waiting times can vary anywhere in between 0 and 5 minutes. So you can actually get 1.23456 minutes. All right, you can get that. 3, by assigning the probability of 0.2 to the height of the vertical line in the figure above, the enclosed area is exactly 1. So what we can do now is answer this. find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. Okay? So when we're thinking about at least 2 minutes, let me see, probability that X is at least 2 minutes. All right? Well, if you think about at least 2, that means the probability of 2 plus the probability of 3 plus the probability of 4 and plus the probability of 5. Okay? Another way to kind of visualize this is by looking at our uniform distribution here. So we have 0, 1, 2, 3, 4, and 5. What we're concerned with, oh, I'm sorry, this is point 2. What we're concerned with is 2 or more. And since this is a rectangle, we don't have to go through this mess right here, which is adding up each individual probability. I mean, you could if you wanted to. All right, it's going to be 1/5 plus 1/5 plus 1/5 and all that good stuff, all right? But we know since this is uniform, we can just find the area. So this is going to be from 2 to 5 is 3 total units, and the height of this rectangle is 0.2. So area is going to equal 3 times 0.2 or 0.6. So the probability that a randomly selected passenger has a waiting time of at least 2 minutes is 0.6. So it looks like you could, on average, you can kind of expect to be waiting at least 2 or more minutes because 0.6 is a little bit greater than 0.5, which would be half. Okay? So now, if we take that idea, all right, and this idea of a uniform distribution, okay, we can apply that to the standard normal distribution. And here's what I mean, all right? It is very difficult to find areas underneath the standard curve. We need calculus for that. However, we do have tools that allow us to estimate the area. So, real quick, let me show you what I mean. Here is the standard normal curve, just like this right here, okay? And let's say, for example, you were concerned with this value right here, which I'm just going to label A. I don't care what it is, all right? But we know that we have to find this area inside this region. Well, sometimes you got to be able to think about solving a problem that you've never seen before using the tools that you've had. That, in essence, is mathematics, okay? Now, we know there is no formula to calculate this shape or the area of this shape, but that's okay because what we can do is we can estimate. So I want you to see what I do right here, all right? So I'm going to get out a different color, and I'm just going to draw what I know is a rectangle. Now, I could easily find the area of this rectangle here. In fact, let me shade it in, and let me zoom in so you can see it. I can easily find the area of that rectangle, and I can go ahead and draw another rectangle and find that area. I could draw another rectangle and find that area, and I can do this for this entire shape. All right, I could do this for this entire shape here if I wanted to. All right? But the problem with this is, and hopefully you're seeing this, this will be an over estimation, but that's okay because it gives us an estimation. It gives us a really good idea of what that probability actually is. Remember, area under the curve is, there's a relationship between area and probability. So we could totally overestimate the area if we wanted to. In fact, we can even do this. So I'm just going to draw it again. I'm going to label this A. And instead of me drawing the rectangles like I did, why don't I just do it like this? Watch this one. Now, like I said, this right here, what we're doing, you're actually, I'm showing you the the fundamentals of calculus here. All right. So notice with this situation here, and I'm going to zoom in for us. And I'm gonna just use a different color here so you can see. I'll use what's a good color? Do I have any cool ones? How about this pink one? Notice here what I'm shading in. These are underestimations, all right? So this is going to give me an under estimation. Okay? So if we think about this critically now, we know that the true area, so I'm going to write true, has to be somewhere in between the area in red and the area in blue. It got to be somewhere in between there. But like I said, that in order to solve that, we would need calculus. Luckily for us, there's been so much studying within this field of statistics that we can go ahead and we can use technology, which I'm a huge fan of that. And we can also go ahead and use some tables, which I'm going to upload up into Blackboard, and I'll show you. So we'll go over this one more time. The standard normal distribution is a normal distribution with parameters mu equals 1. Oh, sorry, that's a typo. Woo! Glad I read that. That is a typo. Mu equals 0. And the standard deviation equals 1. And the total area under the curve is equal to 1. We know it's very difficult to find these areas because it's a curve. All right, and it requires calculus. But we're going to go ahead and we're going to use what we call a z-table. And instead of StatCrunch, these are my notes from last semester. We're going to be using the statistics analysis learning tool, SALT, and I'll show you how to do that. It's very, very simple. All right? But there is something that we have to be aware of. When using the table, it's essential that we understand the following, okay? The table that we use is going to be for standard normal curves. So if we have to standardize our data, then we're going to have to do that. All right? 2, be aware of the table. Area. So when we look at this table, the area is cumulative, meaning it is added from left to right. And I'll show you what I mean once we look at the table. And each value in the table represents area. So each data value in this table is going to represent area, which is the same thing as saying probabilities, because there is a relationship there. And that's the same thing as saying percentiles as well. So those percentiles are going to come back. We're going to visit them. Now, to avoid any confusion, there are 2 things we got to be aware of. First, a z-score is a distance along the horizontal scale or axis. All right, I'll just write axis. That's fine. All right, area is the region under the curve. Now, if you're using the table, which I'm going to show you here in a second, it's going to be the numbers in the body of the table, okay? So I think what I need to do is show you what this table looks like. All right, I'm back. Now, this table you can find in Blackboard, okay? And this is the negative z-score table. In fact, there's 2 of them. This is the negative z-score table, and then you got the positive z-score table. Now, let me show you the difference and why we have a negative and a positive. So I'm just going to go up here. I'm going to zoom in. So clearly in blue, you can see we have our standard normal curve. And right down the middle, oh, that's a really thick pen. Hold on one second. Right down the middle here, mu is going to equal 0, and our deviation for this is equal to 1. So anything to the left of 0 are going to be negative z values, because remember, z-scores are a measurement along the horizontal axis, all right? It's a distance along the horizontal axis. So anything to the left is going to be negative, and then if I scroll down real fast, let me scroll down real quick. Anything to the right of 0, all right, is going to be positive. So notice we have negative z-scores and we have positive z-scores. Also notice the words that they use. Cumulative area from the left. Even if I go over to the negative side, cumulative area from the left. And that's why the shading starts on the left-hand side and we go from left to right. Okay? So now, I'm going to show you how to use this table to find z-scores first. I think that's going to be really important. All right. So let's just say I wanted to find a z-score that is equal to negative 2.31. Okay? So in order for us to do this, negative 2.31, notice that, and I'm gonna use my highlighter here so you can see what I'm talking about. So notice that across the row, it says Z, and you have 0.00, 0.01, 0.02, 0.03, and so forth. And then down the first column, so I'm highlighting again if you can look, we have negative 3.4, negative 3.3, negative 3.2, and so forth, okay? So if you want a z-score of negative 2.31, what you need to be able to do is match this up. So I'm going to use green. So first thing is we need negative 2.3, because if you think about the very first column, this gives me decimal places to the 10th degree. However, across the column, that's where the 100th position comes into play, okay? So if we wanted negative 2.31, I'm going to go to negative 2.3, which is right here, okay, in the lower left-hand corner. And then I'm going to go over to 0.01 because that's going to give me, and I'm going to write it out here. Let me change my pen real fast. Negative 2.3 plus 0.01 is negative 2.31. Now, all I have to do, oops, sorry. Let me go back. All I have to do from here is just kind of drag my highlighter over and drag it down until I intersect. And the value at which I intersect is right there at 0.0104. So if I ask what is, if I ask what is the area for a z-score of negative 2.31, well, you would say 0.0104. Okay, and that's how we use the z-score table. So you can use this table or you can use calculus, but I'm not going to show you how to do the calculus part. All right, like I said, that's beyond the scope of this course. If you're interested, I've taught and we offer a advanced statistics course where you're going to actually use calculus to find all these values. For us, it's great. We got a table. All right, so let me do another one here. So let's see here. Let's find the area when z equals 1.6, we'll say 1.63. So this is going to be a positive value. Now, if you're thinking about this correctly, notice z is positive, which means it's on the other side of 0. So if I were to draw this, where we know 0 is down the middle, that's what makes this a standard normal curve. Since z is 1.63, that's going to be on the right-hand side. It's going to be on the right-hand side of 0. So areas are taken from left to right. So notice I shaded more than 50% of my graph. So my answer, the area, when I go ahead and I write this down, it better be larger than 0.5 because I shaded more than half. So since z is positive, we need to go to the positive part. So here's positive, and we wanted 1.6, what was it again, 1.65? Nope, sorry, 1.63. So 1.63, I'm going to go ahead and use my highlighter here. So here's 1.6, and there's the 3, and all I have to do is just bring these together. And as you can see here, we're going to come up with 0.9484. All right? So the area is going to equal 0.9484. Okay? And that is how we use this table. All right? This table is unbelievably powerful. So what I want to do now is I want to go back to our notes and I want to look at notation. All right? So let me change my pen and let's go back to our notes here. Because we do got to be concerned with notation now. All right? So notation. So if I'm interested with finding the probability that Z is less than A. All right? So what does that look like on a graph? Well, that's going to look just like this. Or that's going to be my letter A. So it looks like this. And the way that we read this is the prob, or probability, that Z is less than A. So if you can have the probability of Z is less than A, you can also have the probability that Z is greater than A. So if Z is greater than A, now watch the picture that I draw, because you got to be careful. I'm going to use the same exact standard curve. I'm going to put A right there. But now Z is greater than A, which means we're on the other side of A. All right? So you're going to shade the opposite side. All right? And this is the probability that Z is greater than A. And we're going to look at examples where we actually have to do this. All right? Because you got to be careful. Now, the last notation we have is that Z can be anywhere in between A and B. So here's what we're looking at here. The probability that Z is between A and B. Now remember, Z is a horizontal distance away from the mean, all right? And A and B are going to be boundaries. And the area under the curve is directly proportional to the percentile or the probability. It's all the same. So this looks like this. So I'm going to have to draw it down here. So here's A, here's B, and this is the probability that Z is in between A and B. Okay? So just let me write that here. Prob that Z is in between A and B. All right? All right, so I hope this is making sense, because this is all just about setting things up, okay? So what I have here is I got a word problem with a bunch of different examples. Now, I literally just stole these examples out of a book, so that's okay. Don't turn me in for plagiarism, but it's good enough for us. So what we're asked to do here in problems 9, 10, 11, and 12 is find the area of the shaded region. So each graph depicts the standard normal distribution of bone density scores with a mean of 0 and a standard deviation of 1. Okay? So our goal right now is just to find what these areas represent. So as you can see in problem number 9, we have a z-score of 0.44. So if we wanted to, we can go back and use our table and look that value up. Whatever we find that value, the body of the table is going to tell me the area under the curve. So it's going to give me this ugly green shaded color. But it's also going to tell me the probability. But all I'm concerned with first is just the area. So for this one, area is going to equal. So let's go over to our z-score table. And we want a z-score of 0.44. So let me write this down. So z equals 0.44. That's larger than 0, okay? So I got to look over here. So right here is going to be 0.404. So there's 0.44. And all I'm going to do is just kind of bring these together. And I found, let me zoom in, sorry. There you go. There we go. So area is going to be 0.6700. So I'm going to go back to our problem. Oh, wrong button. Area equals 0.6700. Okay? Now, some of you may be asking yourself, well, how do you do this using salt? So let me show you. It's so easy. All right, so here we go. Here's salt. Now remember, we're talking about the standard normal distribution. So we need distribution calculators. So I'm going to click on that, and voila. We already have a standard normal curve staring us in the face. Now, in the upper right-hand corner, you're going to see left tail, right tail, both tails, or between. So if we go back and just look at this picture, so let me go back and look at the picture I provided. Notice this is going to be a left tail because we shaded on the left-hand side of that value, okay? So it's going to be a left tail. So make sure left tail is selected. Now, distribution selection, well, we want normal. Our mean is 0. Standard deviation is 1, so that makes this standard. Okay? And then you have options. You can use the probability or we can use z-score. So what we're going to do is we're going to use z-score. So I'm just going to erase this and I'm going to type in 0.44. And notice when I type in 0.44, it shades appropriately. And then right here, let me highlight it on the left-hand side of your screen, are the numbers 0.67003. Now, anytime you use technology, it's going to give you a much more accurate value than the table, because the table can only display four decimal places, and this gives us 5. My thing is this: keep as many as you want until the very end of the problem, and then round to whatever the problem wants you to do, okay? So as you can see right here, a z-score of 0.44 gives us an area of 0.6700, which is fine with me. Now, if you go ahead and you're looking at your notes, the next problem is going to be z equals negative 1.04. However, this is shaded on the right-hand side. So if you were thinking about, well, what does that look like probability-wise? Well, this is going to be probability that z is greater than negative 1.04. So notice here we shaded on the right. So I'm going to do this both ways. I think the first way, let's use salt, because it's going to give us the answer and we can just write it down. And then the second way, we're going to do the table, because it's really important that we know how to do that. So let's go back into salt. Now, we want the area on the right-hand side, so we're going to click on right tail. And then we just come down here to our z-score, and we're going to type in negative 1.04. Okay? And notice that, was it 1.04? Yeah, just making sure. And notice here that the area is 0.85083. So I'm going to go ahead and just round it to 4 decimal places. So it's going to be 0.8508. Now, let's go back to our notes. We're going to write area equals 0.8508, okay? But now the question becomes, okay, well, how do we do this with the table, all right? So notice our z-score is negative 1.04. So let's go to our table. I'm going to erase this real fast. I'm going to zoom out so I can move up. All right, here we go. So I am very, very particular with how I do these things. I always draw a picture. So let's go ahead, let's draw a picture here. So negative 1.04 is to the left of 0, and we need to shade to the right. Now, here's what we know. We know 2 things. We are guaranteed 2 things with this table. First and foremost, they give you z-scores, and z-scores is a measured distance along the horizontal axis. That's number 1. Number 2, the area is always added from left to right. Therefore, when I go ahead and find the z-score for negative 1.04, which is going to be, here's negative 1.0, there's the 0.04. So notice it's going to give me an area of 0.1492, and I'm going to write that in the upper left-hand corner. Okay, but here's what I actually got, all right? Here's what we got. I'm going to change the color, and I'm going to write it right here. See, it gave us the left-hand side, but we don't want the left-hand side. We want the right-hand side. So this is where the theory kicks in. Well, we know the total area under the curve, so area total, is equal to 1. If you know the left-hand side, all you need to do, actually, let me write it like this. So z is greater than negative 1.04. All we need to do is take 1 minus 0.1492. And that's going to give me the area that I have shaded in black. So if I get out my calculator here, there we go. There's a calculator button. And I take 1 minus 0.1492 and hit enter. Notice I get 0.8508. Okay? So we get the 0.8508. In fact, let me write it in the body of my graph here, 0.8508, which is what we wanted. So you got to be really careful when you're doing this, okay? Because sometimes you want area to the left, other times you want area to the right. How do you know which one you want? Draw a picture. Draw a picture if it's not provided. Make sure you read the question. Make sure you understand what the question's asking you. So let's go ahead and let's do the next one here. We're going to do problem number 14. I got to find my notes. There we go. So problem number 14. Now notice we want z in between two values. So we want to find the area in between these two values here. All right. So I'm going to do this both ways again. Let's use salt first because that's the easy one. So let's open up salt. Everything stays the same except on the upper right hand corner, we don't want left nor right nor both tails. We want the area between. So when I click on between, notice in the lower left hand corner, we have Z1 and Z2. Okay, Z1 and Z2. See if I can zoom in here a little bit. There we go. So all we need to do is just go ahead, go ahead and just type in what our Z scores are here. So the first one is going to be negative 0.84. And then the second Z score is going to be 1.28. Now directly above, notice 0.69927, which if we rounded that, okay, if we rounded that, we're going to get 0.6993. So I'm going to go ahead and write that down. And let me, oh boy, I just screwed that up because my fat fingers got in the way. So let's do this again, 0.84 or negative 0.84 and then 1.28. And now I'll zoom out. There's our picture. Notice in your notes, it looks the exact same. So let's go back to our notes. And I'm just going to write area equals 0.6993. And this is from salt. Okay, I want to highlight that. That's from salt. Because when we go ahead and do this using our table, all right, we actually are going to get a number that's a little bit different. And it's not much different, but you'll see. All right. So let's go ahead and let's use our table. So let me get out my table. Here we go. I'm going to erase this real fast. So erase, erase, erase. And I'm going to write down the Z scores. Z equals negative 0.84, and then Z equals 1.28. Okay? So off to the right-hand side here, I'm just going to write Z equals negative 0.84. Area is going to equal, and make sure you just draw your curve real fast. Make it look nice. Notice I'm not that particular, but I make sure it's good enough. So area for negative 0.84. So here's negative 0.8. There's my 4. So I'm going to zoom in so you can see what's happening. So I'm going to draw this all the way down, draw this all the way to the right. And I come up with 0.2005. So that's the area for a Z score of negative 0.84. Now we're going to do the same thing, but we're going to do the Z score for 1.28. So since that's positive, we got to go to the positive Z score table. So Z score 1.28, we got to go down to the positive Z scores, and I'm looking for 1.28. So here, sorry, my dog's barking in the background, but we're all accustomed to that by now. So here's 1.2. All the way in the far right-hand corner, upper side, is going to be 0.08. So let's just go ahead and draw the line over and draw the line down. So notice we get 0.8997. So I'm going to go ahead and write that number up above. 0.8997. So area equals 0.8997. Now, since we want the area in between these two numbers, all we have to do is just take 0.8997 and subtract 0.2005. And when we do this, 7 minus 5 is 2, 9 minus 0 is 9, 9 minus 0 is 9, 8 minus 2 is 6 with our decimal point. So notice, when I'm using the table, I get 0.6992. So I'm only off by 10 hundred 1/10,000. I'm only off by 1/10,000th of a decimal place. But the problem is you're going to get different answers. Do not get bogged down with the fact that one is 0.6993 and the other one is 0.6992. All you're going to do is end up driving yourself crazy. Anytime you use technology like our SALT tool right here, you're going to get a more accurate answer. All right? The table can only give us 4 decimal places. So I hope this made sense. And there are a couple more examples that I want to go over. So let's go ahead and let's look at them real fast. So here we're going to find the indicated z-score. So notice here I'm giving you the area underneath the curve. I want to know what is that distance away from 0. So now we actually have to, and we can use SALT or the table for this. But remember from previously in the lecture, you got to make sure that you're understanding what we're giving you. Anytime I give you an area, that's the body of the table. All right? So let me show you how to do this real fast. So I'm looking at the body of the table. So just give me a second here because I'm going to erase all this stuff real quick. There we go. Now, I'm instantly going over to the positive z-score because our area was 0.89. What was it again? 0.890? Yeah, 0.8907. So it's bigger than 50%. So I know I got to be beyond the mu of 0. Now, I need to try to find in the body of the table, and like I said, this is the stinky part, using a table, is you got to find 0.8907 or as close as you can to 0.8907. So I'm going to kind of help us out here. If we look right here, so let me just zoom in real quick. So notice I found 0.8907 amongst all these crazy values. And I'm going to go the exact opposite way. In other words, I'm going to go outward. And by going outward, that gives me the z-score. So the z-score for this problem would be 1.23. Now, I'm going to just write that down in our notes, and then I'm going to show you how to do this using SALT. Okay? So z is going to equal 1.23. So how do you do this using SALT? Watch how easy this is. You got to love technology. First, we know from the picture, it's a left tail. So I'm going to click on left tail. Second, where I have this equals the probability thing, so I'm going to highlight it. It's on the left-hand side of your screen. I can zoom in here for us. I'm going to type in 0.8907 and just hit enter. Oh, sorry, wrong keyboard. 0.8907. And when I do that, look directly underneath. It says z-score equals 1.2303. So using SALT is so much easier because you don't have to worry about trying to find it in the body of the table. All right. All right, so let's go back, look at a couple more problems here. And I figured I'm going to let you go ahead and do the other problems that I don't do, only because if you look at the solution notes, they're going to have the answers, but I really want you to kind of figure this out on your own, okay? So you can go ahead and do 13, 14, 15, and 16. So the last thing that I want to kind of look at here is I'll do one of these questions here. So assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0, standard deviation of 1. In each case, let's draw a graph and then find the probability of the given bone density scores. That's going to be less than negative 1.23, less than 2.56, or greater than negative 2.0. So I'm going to go ahead and I'll do part B. So the first thing you want to do, just like the previous problems, you always want to draw your standard normal curve. Put 0 right down the middle. Now, we want less than 2.56. So I draw a line to the right of 0, because those are positive values. And I'm going to label it 2.56. And then I'm going to do my shading, because I went less than, so I'm on the left-hand side. And then you can go ahead and you can use SALT, or you can use the table to go ahead and do this. I'm going to use SALT. So I want a left tail, and I'm going to change my z-score to 2.56. And I find that that is an area of 0.9947 or 0.9948, we'll call it. So let me go ahead and write that down. So the probability that z is less than 2.56 is going to equal 0.9948. Okay? And that's I mean, honestly, that's as hard as this gets. It's just understanding what you're given and then applying the technique for it. Okay? So you can go ahead and try these other ones, like all the way down to letter E. I'm going to go ahead and do F and G for us because those two are, students tend to have the most trouble with them. But like I said, if you go back and you think about what the area under the curve actually represents. So I'm going to write it off to the right here. Area, remember, is percentiles or probability. They're all the same. Okay? It's just calling it a different name. So if we want to find P99, that is the 99th percentile. So that's going to be the number that separates the bottom 99% from the top 1%. So if we think about this, U is right down the middle. Draw a normal curve. And since I'm asking for the 99th percentile, percentiles correspond to areas. All right? So what I want to know is if I shade all of this, and this area underneath this curve represents 0.99 or 99% of the area, what does this z-score have to be for that? All right? And if you think about it, that's exactly what the question is asking for. They're asking for what is the bone density score? Well, that is going to be a z-score. So let's go ahead. I'm going to use SALT again for this. So I want a left tail. And inside where it says probability, I'm just going to type in 0.9900 because I want 99%. And that z-score is going to be 2.3263 or just 2 point, and I'm going to round it to 2 decimal places. 2.33. So this z-score is 2.33, which means a bone density score. So actually, instead of just saying it, I'll write it. A bone density of 2.33 separates the bottom 99% from the top 1%. Okay? So now for part G, because G is it's not the special case, but it's the only one we didn't do yet today. All right? And I'm going to do this using the table and using SALT as well. So if bone density scores in the bottom 2% and the top 2% are used as cutoff points for levels that are either too low or too high, find the two readings that are considered cutoff values. In other words, we need to find the bone density scores that separate the bottom 2 and the top 2%. So I draw my normal curve, and we have a too low and a too high cutoff point. What we want to know is how far to the left and how far to the right do those z-scores go. Okay? So if you think about it, once again, I'm giving you percentages. Percentages are areas. So this has to be 0.02 because I want 2%. All right? Now, if I shade this, remember, areas are taken from left to right. I also need to find the area up here in the upper right-hand corner. But that's going to be 1 minus 0.02, which is 0.98. Okay? But here's the beautiful part about using the standard normal distribution. At the very beginning of the lecture, I gave you some properties about this curve. One of them was mu equals 0. The second property was your population deviation equals 1. And then the third is that bell-shaped curves are symmetric, which means if I find one side, like the left-hand side, then I can apply that to the other tail or the outside tail. All right? So let me show you what I mean here. So I'm going to go ahead and use the table. All right? And since this is 0.02, we know that's negative. It's on the left-hand side of 0. So what I need to do is I need to go ahead in the body of this table and find 0.02. All right? Now, remember, you're looking for 0.02. So that's going to occur right about here. All right. Notice right here, and I'm going to zoom in here for us. Notice that says 0.0202. It's not perfect, and that's okay, but you need to get as close as possible to 0.02. This is where the table gives that ambiguity, because it's only as good as the data that's on the table. When we use SALT, we're going to get a better answer. But notice here, the z-score cutoff for that is going to be negative 2.05. So if I go back into my notes or into our problem, this cutoff value that's too low is going to be negative 2.05. And because of symmetry, this too high has to be 2.05. Because remember, we're using the bottom 2% and the top 2%. But just to prove to you that it is 2.05, let's go back to the table. We're going to look up the z-score of 2.05. And that should give us an area of 0.98, which is what we calculated before. So let's just go ahead and get rid of this. Here's 2.05. That's right there. And as you can see, as I come down, notice I get an area, and I'll zoom in for us, of 0.9798, which is, if you round it to 2 decimal places, 0.98. Okay? So I hope this makes sense. I'm going to show you using SALT, because SALT we love. So here's SALT. Now, upper right-hand corner, notice left, right, both tails, but what we need, or in between, we need both tails. And let's go ahead and just type in for our area 0.02. And by doing that, look what happens to my picture. Not only does it separate it for us, but it looks exactly like the one that I drew. Also, excuse me, when we look at the probability here, we went 0.02, and notice our z-scores are negative 2.3 and positive 2.3. So there is where we get a little bit of ambiguity here. Oh my gosh, I'm so sorry. I made a mistake here. I actually made a mistake. And I don't normally do that too much, but I made a mistake. So we need to be careful, and I was not careful, and here's why we need to be careful, all right? If I'm looking at this graph right here that we have, in fact, let me go back to our picture, all right? I'm going to go back to our picture real quick. I circled this because that area in this region right here, in the lower region, is 0.02. However, I forgot to take into account that this area on the top is also 0.02. So when I go and use SALT, I can't believe I made this mistake. I know why, because I'm starving right now, to be honest with you. The probability is not 0.02. That's only for one tail. The probability, or the percentile for this area, is actually 0.04. And notice now, everything fixes. Negative 2.05 and positive 2.05 in terms of z-scores. I'll zoom in here for us so you can see it. So that was Professor Float's mistake. Please don't be me. Don't make that mistake, okay? But that's going to be it for this lecture. I know it's a really long one. And if you think about it computationally, it's very easy. It's all about interpreting the question, okay? So if you have any problems, please let me know. And what I'm going to do is make another video here for us that deals with sections 2 and 3 at the same time, because they're actually really easy. So I'll see you next video. Bye.